Opioids are a class of drugs naturally found in the opium poppy plant. They include the illegal drug heroin, synthetic opioids such as fentanyl, and prescription pain relievers such as oxycodone and Vicodin. Opioids work by blocking pain signals between the brain and the body, but in addition to that, opioids can make some people feel relaxed, happy, or high, and can be addictive. Symptoms of opioid addiction include inability to control opioid use, drowsiness, weight loss, changes in sleep habits, and is potentially fatal. The opioid epidemic started in the 1990s when pharmaceutical companies claimed prescription opioids are not addictive, totally safe, and doctors prescribed opioids to treat even minor pain. The problem continues in the face of the huge profits these companies are making. Data from the CDC shows that the overdose death rate of opioids increased by more than 500% over the past 20 years. Even President Trump has acknowledged it as
a tremendous problem in our country, and we're going to get it taken care of as well as it can be taken care of, which hopefully will be better than any other country which also has these same problems or similar problems.
And as Trevor Noah said in The Daily Show,
the opioid crisis is as American as baseball or student loan debt.
Access to medications for opioid use disorder is critical to reducing overdose deaths, but the impact of improving access to these resources on health outcomes can vary substantially in different local conditions under various policies. This is the context of my work this summer with Marynia and Qinyun as part of a NIH-funded JCoin project. We are trying to decompose the impact of access to resources on regional opioid use disorder into different policy scenarios, using the variation of policy over time and space. To do this, policy landscape will be abstracted into quantitative datasets. Then a quasi-experimental longitudinal analysis will be conducted, and finally the result will be used to inform future place-based policymaking. I focused on the first step, building the datasets for access to medication for opioid use disorder. My first task is to recover data from PDFs containing information of drug and alcohol abuse treatment programs from 1975 to 2019. They detail the name, address, contact information, and services provided by each unit in the form of abbreviated codes. At first, the task seemed easy. Just take out the text and split them, which can be done by many Python packages, but turns out it isn't that simple. PDFs before 2000 are scanned from old files, and they contain noise and vague characters that mess up the character recognition. Even if the character recognition is done correctly, incorrect line breaks can cause the data of several units to be mixed up. And even if all the data are scripted correctly, the splitting is not as simple. Things like titles, subtitles, and page numbers often get in the way. Then I realized that the position of the words were lost with the simple packages that only returns text and line breaks from the PDFs. Using the fifth package, I extracted both the text and their position. This metadata enabled me to easily identify and ignore page numbers and titles, and split data into information about each unit. After that, the information contained in each line is labeled by their characters and the label of the lines before and after it. For instance, if a line has a comma followed by 2 capitalized letters and 5 digits, it is labeled a line with city-state information. And if a line contains words such as avenue, P.O. box, or numbers and is before the city-state line, it is an address line. Some of these criteria are loosened a bit to accommodate the misrecognized characters. For example, this comma might be recognized as a period, or missing completely, and this digit might be recognized as a letter. But character recognition is still the biggest error source and could be a whole other project. Using this method, I created a pipeline that scripts a PDF of around 1,000 pages with data of over 10,000 treatment units in under 20 minutes. From this data, we could already compare access to different medications each year, or plot and see the changes in the number of treatment units with MOUD on the zipcode level. But the spatial correlation of policy and effect would be best addressed by an access model to these medications. So my second task was to calculate zipcode level access scores. In an access model, the access score for each location is calculated based on a function of distance decay, weights of different facilities, and the penalty for same types. It is also dependent on the means of transportation selected. Using the spatial access package, spatial access for each year could be calculated. Future work for this project includes finishing the spatial access correlation and running correlation models. and hopefully the results could be used to make changes that influence people's lives.